So this example problem of continuous beams will help you to understand design of beams, whether they are singly or doubly reinforced or rectangular and T-beam or edge beams. So all type of beams what we have discussed, when you will design a continuous beam, you will get idea about all type of cross sections, rectangular and T, as well as in terms of behavior singly and doubly, both you may require to design the cross sections singly or doubly at various critical positions. So in a way, this topic is actually a comprehensive review of what we have discussed under the heading of beams design, not only flexure but also shear design of beams. So this example is taken from the third edition of Z. Siddiqui book, chapter 4, example 4.5. It describes a slab system, which is a roof slab, and this roof slab has columns at a spacing 5 meter center to center along x-axis and 3.5 meter center to center along y-axis. So it is mentioned in the statement that there are more than 3 spans at a rate of 5 meter center to center along x-axis, and there are more than 2 spans. You may say 3 or more, but it is mentioned that this slab system has more than 2 spans in x and y direction, because for 2 spans coefficients are different, and for more than 2 spans we need to select the azimuth coefficients. And furthermore, it is stated that this slab system is resting on a beam column frame structure, and columns are 9 by 9 inch in cross section, 228 by 228, and beams are running on column center lines. 2 of the beams along x-axis are marked on this plan, beam layout plan, and there are 2 more beams which I can mark, like this edge beam along y-axis. I may mark it like B3, and this interior beam along y-axis B4. So if panels are equal in size along x-axis and then they are equal in span along y-axis, then the exterior beam B1 along longer span and then B2 along longer span will be repeated until we get the other side of the other edge of the slab. So B1 will become the replica of the other edge, and B2 will remain valid for all interior beams along x-axis. Similarly, B3 will be the edge beam along y-axis, and B4 will become valid for all interior beams. If slab system is square, then along x and y direction almost same edge beams and interior beams design will become valid because load distribution will remain the same in X and Y direction if panels are square, because triangular loads will be transferred to the beams. It is further given in the statement that on this slab, the ultimate load is 12 kilonewton per meter square. So actually, it is not only the load on the slab, but it includes the self weight of the slab plus the floor finishes self weight plus the live load which will be placed on this slab. So selecting a combination like second combination 1.2 dead plus 1.6 live, this 12 kilonewton per meter square is proposed as ultimate load, which includes the self weight of the slab plus floor finish plus the occupancy load, live load. And it is also mentioned in the statement that in this slab system, slab thickness is 5 inch, 125 millimeter. And since column sizes are 228 by 228, so width of the beam selected is 9 inch, equal to the column size 228 millimeter. So BW of the beam is exactly equal to the width of the column. It is proposed. So short span is given the notation L with subscript X 3.5 meter and long span L with subscript Y. Material strengths are also given 20 and 420 megapascal for concrete and steel respectively. So in academic problems, just practice problems for uh, students. In a question, you are given with all this kind of data that this is the slab thickness and column size and selected material strengths, and then finally estimation of the ultimate load on the slab. But when you will perform designing in design office, it will be actually your job to design the columns. You need to fix the cross sections. It will be your job to select the slab thickness because slab design will be done by you. You will be given with the architectural drawings, and in architectural drawings you will only get the dimensions, plans, and the cross-section dimensions, beam cross-section, slab thickness, column cross-section, footing size, that will be done by you. There may be some restrictions from the architect that the maximum column size may be not more than this. It may be his recommendation, or the maximum recommendation may be that he or she wants circular or square geometry in columns. There may be a restriction that beam drop below the slab should not be more than this limit. But then finally you have to select based on serviceability requirements and selection of beam as singly or doubly. So this 125 millimeter slab thickness will be actually fixed by you. Column size will be your actually job to design the column to fix the cross section. Selection of material grades will also be decided by you. Knowing the type of project and the cost involved, you will decide the material strengths. And once all these designs are done, from architectural drawings, you will be knowing that how much floor finish thickness architect is proposing and type of floor finish proposed. So according to the thickness of the floor finish proposed by architect and the type, you will select the densities and then you will determine the pressure load. Also, knowing the type of building, you will select the live loads. So in this way, after doing this exercise working, you will get this 12 kilonewton per meter square, which is given directly here. Moreover, in this academic problem, practice problem, we are asking you to design B2 only. First interior beam along longer span. But in actual project, you will not be engaged for just one beam design. You have to completely design this slab system. Not only slabs, panels, corner panel, edge panels, interior panels, but also all the beams, then columns, then footings. So it will be a complete design, not just one floor, maybe it is a multi-story building, so all the floors. So we at the moment are only focusing on design of first interior beam running along the longer span, B2. It is further mentioned in the statement that live load, service live load over service dead load ratio is maximum equal to or less than 3. So this is one hint given to you that actually you are allowed to check limitations of ACI moment and shear coefficients. So in ACI moment and shear coefficients, one of the limitation is in order to apply those coefficients that live load over dead load ratio should not be more than 3. This is what they are stating, that indirectly they are giving you permission that if other limitations as well are satisfied, then go for the simplified analysis of the continuous beam. Few other limitations are spans should not differ by more than 20% of the shorter span. So in this problem, all spans are equal. Loads are uniformly distributed. So this is a slab system. There is no, you can say, varying load or point load. So loads are uniformly distributed. It is for gravity loads. So dead and live loads are present. There are no lateral loads. Beam cross sections should be prismatic, so not for varying cross sections these coefficients are applicable. So obviously you will finally select the prismatic sections, so you are not going to vary the cross sections within spans. So more or less all the limitations of movement coefficients are fulfilled, so you are allowed indirectly to select ACI movement coefficients, or if you are not interested, then you may perform analysis by using any classical method, or you can perform finite element analysis and design. So you will model this frame and then accordingly you can analyze and then design by using any commercial software. But we are actually, for this example problem, we are going to apply the ACI movement coefficients. Now, in one of our topic of load transfer path, I have discussed with you that if slabs are one way, two way, how load will be transferred to the beams. Here in this case, if I determine the aspect ratio, longer over shorter span of the panel, I get the answer less than 2. So panels, all the panels are two-way, and panels are resting on the beams. So it is a beam column frame structure. So we studied that if slab is two-way, we will draw lines at 45 degree from corner of the panels, and where they intersect, we will divide the panels into segments. So when the aspect ratio is less than 2, we will get division of slab into 2 trapezoids and 2 triangles. If aspect ratio is exactly 1, we will get all triangles. But if it is greater than 1, less than 2, we will get trapezoids and triangles. These segments of the panels will transfer their load to the corresponding beams on which they are attached. Like this beam B2, which is running along the longer span, will get the load from adjacent panels by dividing the panels into segments, and 2 of the trapezoids will transfer their load to beam B2, and onward all the panels, adjacent panels, will transfer their load to the corresponding beams by dividing them into trapezoids and triangles. We also discussed that to analyze a beam with the load present as trapezoid or triangle will be little lengthy, that I will put on the beam P2 two trapezoids, 2 into, if the one trapezoid has the area A, so I will say like this, 2 into A, and I will calculate the mid-span movements or sagging and then hogging movements. So rather to perform analysis with these varying loads, if I can convert them into equivalent UDLs, so that finally my movement magnitude, what I will get by converting these trapezoids or triangles into equivalent UDLs, so that the movement magnitude in both pictures remains the same. So then it was done to convert the trapezoids or triangles into equivalent UDLs by using the equivalent widths, so that I can determine the hogging and sagging movements more easily, which are exactly equal to the movements which I will calculate otherwise by solving the beams with trapezoidal or triangular loads. So this exercise we have done on one example problem. and we derived equations to determine those equivalent widths with which if I multiply my ultimate pressure, I will get the equivalent UDLs. So if you recall, for trapezoids, the equivalent slab width we determined by using this equation, in which R is the ratio of shorter over longer span of the panel, and Lx will be multiplied with this 1 minus R square over 3. And I mentioned in that lecture that there is a common mistake that students think that since the span is longer, so the length which need to be multiplied with this 1 minus R square over 3 will be Ly. They are confused, but in derivation we have seen that to get the equivalent width with which I will multiply my pressure to determine UDL, equivalent UDL, the equation is having Lx, the shorter span, 1 minus R square divided by 3 into Lx. And if I want to determine the equivalent slab width for the beams which are running along y-axis, and suppose I am talking about this beam B4, which is taking triangular loads, then there are two triangles which will be transferring the load on this beam. Then the equivalent width to determine the UDL we derived was 2 by 3 into Lx. You can check your notes or recorded videos where we derived this equation for the beams which are running along the shorter span in slab panels. And if slab panels are square, so for all beams we will get, for all interior beams we will get 2 by 3 Lx, because then there will not be any trapezoid in the slab system. Here in this problem, since we are asked to design a beam along the longer span, so the equivalent slab width which we are going to apply is 1 minus R square over 3 into Lx. Also, it is important to note that this is a slab system with regular T-beam construction where web of the beam will be projecting below the slab. There are some slab systems in industrial buildings when beams are very deep, and to save the vertical space, they are going to project the web above the beam. So inverted T-beams are designed with the web projected above the slab. So not very common in commercial or residential buildings. However, in industrial buildings for long spans on roofs, slabs, this inverted T-beams are commonly used. In this problem, we are asked that a roof slab is with the beam projection below the slab, and beams are cast monolithic with the slab, so it is a T-beam construction. In the given factored slab load, the web of the beam projecting below the slab, its load is not included. In the statement, what they are stating is that the slab factored load is 12 kilonewton per meter square. If in the statement it is given that this 12 kilonewton per meter square includes not only the slab load but also the beam stem load projecting below the slab, then we need not to take into account the extra load which will be present due to self weight of the beam. So since in this statement they are not mentioning that this includes the self weight of the beam projecting below the slab. So what is the first step? We are calculating approximate self weight of the beam stem. In order to determine the approximate self weight of the beam projection below the slab, because we have to design this beam also, at the moment I only know about the width of the beam which I fixed as it is equal to the column width 228 millimeter, but regarding its depth I have no idea because I have to proportion it finally for design purpose. So a very conservative selection of the beam gross depth will be, which will envelop almost all the serviceability required depths to get the deflections within limits to keep the crack widths minimum, and serviceability based H. If you consult the table given in chapter 9, you will get based on various end conditions and steel grades the recommended depth of the beams. Out of them, if I select one conservative selection which is span by 12 as the edge of the beam, it will fulfill almost all the requirements. So a tentative H is selected in this problem in order to estimate, in order to approximately estimate the self weight of the beam. So what is done? Cross-sectional area of the beam will be B into H, which is span by 12. But in this span by 12, when I will determine H, it will also include the slab thickness, which has been considered in 12 kilonewton per meter square. So in order to eliminate its contribution, which already is considered in 12 kilonewton per meter square, out of this H equal to the slab thickness, we normally use HF for this, height of flange is subtracted, so that we will finally get only the stem below the slab. So span by 12 minus 0.125 will give me this depth below the slab into B into 2400 kg per meter cube will give me answer of self weight of the beam projecting below the slab in kg per meter, the density multiplied by area. Further, I want to convert this into kilonewton per meter, so I multiplied this with 9.81 divided with 1000. So 9.81 will give me Newton and divided by 1000 will give me kilonewton per meter. Since I am doing ultimate stand design, and that is the reason factored slab load is given to me. So the self weight of the beam should also be factored. So I have selected the dead load factor 1.2 to convert the self weight of the beam projected below the slab into factored self weight of the beam. So I got 1.9 kilonewton per meter as the factored self weight of the beam. By assuming approximate H for estimation purpose. Later on, I will check whether my selection was conservative or unconservative. Conservative means that safe. But later on, if your depth will come out to be more than this, then you need to check that whether this underestimation resulted into a serious drop in capacity or still you are safe by rounding up the loads during doing the design. So such estimations are normally done on the safer side because later on you need not to revise your calculations. So it is decided then that equivalent slab width by considering trapezoidal loads transferred to the beam will be 2.93, which will be multiplied with the pressure which was given 12 kilonewton per meter square will give me the ultimate UDL on the beam, because two trapezoids are getting the equivalent slab width 2.93, and as a result I will get UDL on the beam. Here in this problem, author has also applied one factor, that is increasing the load transfer to the beam 10% by considering that the first interior beam will have to support 10% more width than the other interior beams. So that is the reason, over and above one other factor 1.1, increasing the self weight by 10%, increasing the load transferred on the beam by 10% is selected here for first interior beam. However, for rest of the interior beams, if panels are more than 3, panels are 3 or more, even for 3 panels, one beam will be at the center and there will become 2 beams which are first interior and the central one will be the interior. If panels are more than 3, then you will get more interior panels where you need not to apply this additional factor 1.1 proposed here. So this load transferred from the slab as UDL plus the self factored load of the beam stem together has given us a UDL on the beam. So I can sketch like this. It's very difficult to draw straight line with mouse. So we have a beam column frame, and now this beam is subjected to a UDL of 40.5 kilonewton per per meter. Now for this UDL, I will design the beam. Since the limitations of ACI moment coefficients are satisfied, so I will call those coefficients. In those coefficients, it is required to use clear span between the supports for calculation of moments. Further, for different end conditions, hogging and sagging moment coefficients are proposed. This particular example problem is referring to a structural system where beam is framing into the column. Beams are framing into the RC columns. So if I take you to that picture, so this picture is actually valid that beams are framing into the columns. So when beams are framing into the columns, for movement and for shear, the coefficient at the face of exterior support negative movement coefficient will be 1/16, and for shear it will be 1 WL/2 into 1. So I can write like Cm into Wu into Ln square, and Cv into Wu into Ln divided by 2. So Cm and Cv are actually used to determine the moment and shear. So if beam will frame into the RC column, hogging moment will be calculated by using coefficient 1/16, M negative. And the first span or exterior span positive movement will be calculated by using the coefficient 1/14, sagging moment. And exterior face of first interior support hogging moment will be calculated by the coefficient 1/10, and shear will be by coefficient 1.15. So 15% more load is transferred as it is indicated with this 1.15 to the face of first interior support. So more shear is transferred to the face of first interior support, while on exterior support it was WL by 2, but you will get 1.15 as the distribution of shear when you will be selecting the shear coefficients. And interior supports exterior first interior support interior face, first interior support and interior face hogging moment, are all other interior faces of interior supports. Hogging moment coefficients are 1 over 11, 1 over 11, 1 over 11. However, positive movement for all interior spans will be based on coefficient 1 over 16. So keeping in view this distribution here, selection of coefficients for beam framing into the column 1 over 16, for the mid span of exterior panel, exterior span 1 over 14, for the face of first interior support at exterior face 1 over 10, for all other interior supports at the face of supports 1 over 11, and for all interior mid spans 1 over 16. So this is selected, and 5 different sections, 3 for negative and 2 for mid span positive, are calculated by using the clear span, which we have estimated as center to center was 5 for the beam along the longer span. Subtracting half of column dimension from either side will result into the dimension equal to column 0.228. So the clear span will become 4.772. So in this edition of book there was a typing mistake, which I scanned this example from that third edition. So I hope in new edition this typing mistake will be removed. 4.772 is the clear span. So this is what is the hogging. First sagging movement in exterior panel, then hoggings, and finally the sagging. Now we have 5 different sections, and out of them 3 are negative, 2 are positive. Now the question will arise that which out of them I use to determine the minimum, that minimum depth which will result into a ductile section with steel strain 0.005 or bigger when concrete crushes. If I will not be selecting D based on that requirement, then I have to design doubly beams, because over reinforced beams are not allowed. And in order to design singly beam at various moment demands corresponding to them, I need to calculate D. Normally in field construction, we do not vary the cross sections in each spans. So we normally keep the span same. We normally keep the H, the depth of the beam, same in various spans. So it is more practical to fix the H based on highest demand, so that if the highest moment section will get the H satisfied for D minimum, then rest of the sections will automatically be satisfied. But if I will select the lower movement to fix my D minimum, then obviously those sections which are having movement higher than the selected one will enter into either transition or over reinforced domain if I still go singly, which is not allowed. So then I have to go doubly at those portions where D becomes less than D minimum. So it is always preferred to scan the movement demands and out of them select the maximum movement to fix the depth of the beam. It is important to note that when slab is present on top, it is a regular T-beam construction with the web projected below the slab. I am drawing this line to indicate that there is a slab present over here. It is important to note that at hogging regions, tension will be on the top and compression will be on the bottom. And in sagging regions, tension will be at the bottom and compression is on the top. So in hogging regions, when tension is at the top, neutral axis may be somewhere over here. So when tension is at the top, the cross section, whatsoever its shape is, will be ignored because concrete contribution is negligible in tension. So a rectangular section will be analyzed at all sections over the supports because slab in tension will not contribute and the geometry, even though looks like a T shape, is not to be considered in estimation of T value. So T will only come by contribution of steel and C will be calculated by the concrete stress multiplied by area. So over the supports in regular T beams, section will be like a rectangular beam and the D minimum selection will be done by using the equation which we derived for rectangular beam. So this is option 1, which is most suitable. However, in this option to fix the D minimum, if depth comes out to be more, because highest demand you are using to fix the D, and if architect is not allowing to go that much deep in cross section, then obviously there is no other choice except to go doubly in those portions where beam is behaving like a rectangular beam. It means over the supports. So you then have to design doubly beam cross sections over the supports if you are not allowed to select the D based on the maximum demand. So all these options are discussed on this page, selection of beam depth, that many different options are available for sizing the beam. Option 1 may be to size the beam as singly reinforced section for exterior span positive movement. Exterior span positive movement means that you intentionally are sizing the beam based on the movement which is 65.9. So it means based on the 65.9 you are calculating the D, and in this D further you will add the cover to get H. So it means when you will enter the section where movement is more than 65.9, you will get the depth less than what is required at the section with higher movement. So it means with 92.3 you actually require D minimum 315 and you are selecting 266. So it means you have to then design doubly section over the first interior support where movement demand is 92.3. That is what he is stating, that then design as doubly for negative movements. I think that will be accepted when architect is not allowing us to go deep, because second option is what I said earlier, to proportion the section for maximum negative movement, which is more easy because you will definitely get all sections fulfilling the D minimum, and you will be designing singly reinforced sections, and the only problem will be in this case it may significantly increase the beam depth if the first interior demand is much higher than the other sections. Third option what they are proposing is to select the dimension in between, so take average of both. But I suggest you that if the first interior is not too high, as in our case in this example problem as well, the difference between the 65 and 92 is not that much, and if you will select 315 rather than 266, there is not much increase in the minimum, so you should go for second option. In addition to the flux demands, don't forget that serviceability based H need to be checked also against the deflections. So based on serviceability, span by 18.5 is the coefficient for grade 420, and when beam is 1 and continuous, this highest demand will come, and span is center to center, so this will give us directly H, and it means we are well above the serviceability based H, because our flexural based H is 341, or if I add 75 in this 315, I will get answer well above the h which is required for deflection, and for estimating the self weight of the beam. So I'm satisfied that I need not to reconsider the self weight for estimation purpose. So out of them, here author has selected the highest demand, which was based on 92.3, it is 315 plus 75, which is the cover selected for the steel layer from beam bottom to center of the steel layer. So H minimum to satisfy tension controlled under reinforced beam is 390 millimeter. Now this is theoretically estimated H, in which the beam stem below the slab will be 390 just to estimate that how much is the beam stem then below the slab. So it means 390 minus 125. So it will become how much? 290 and then minus 25, 7, 80, 90, 265 will be the beam stem below the slab. So in field, if we want to erect a formwork for casting of the beam web, and we are using stacking up of bricks to make a trench for the beam web, to make a temporary formwork. So what we will do, we will stack bricks one above the other to make a temporary formwork. And for even beam bottom, we will place bricks in a way to make this trench. Which can later on be dismantled once concrete will be poured inside this trench by stacking the clay bricks one above the other. So for that purpose, you know that a clay masonry, a clay brick has the thickness almost 3 inch, 75 millimeter, 4.5 inch wide, 9 inch long, and 3 inch or almost 75 millimeter deep. So if I'm stacking them 1, 2, 3, 4, one above the other to make a temporary formwork, rather than using the plates, I'm arranging them to make a trench within which I will pour the concrete. Then 4 into 75 plus then comes the plate for the slab on which I will pour the concrete of the slab. So here what author has propose you that if you will be working on that practical selection, keeping in view the construction technique at site, so then 4 into 75 plus 125, so it will be more practical to fix the H 425. It means the drop below the slab is 300 millimeter. This is one suggestion. If you want to be more theoretical, then this is fine, 390. A bookish design is quite acceptable at your level, but once you will be finally practicing at site, you will be knowing many field issues, field applications, limitations, common challenges, economical options for formwork. Then it is more possible that you will be selecting the sizes which are more practicable. So that is what is suggested here, that if I am selecting let H is multiple of 75 plus 125, then it will give me overall depth 425, and I am still selecting a cover if 75. It will give me the D in my actual cross section 350, which is well above D minimum. So I'm happy. I'm happy with that selection. This architect has no objection with this 300 millimeter draw below the slab. Then, now it is the time to start designing the beam at various sections. Face of the support, and this steel will be designed. Midspan of the exterior span, this steel will be designed. Face of the first interior support or other faces, out of them higher will cover, and this steel will be designed. All interior supports, this steel will be designed, and interior spans, this steel will be designed. So in this way, 1, 2, 3, 4, and 5 sections I want to design. It is important to note that 1, 3, and 5, when slab is present on top, they are rectangular sections, although apparently they are T-shaped, but since tension is present on top, so still you will be dealing with them like a rectangular beam design sections. However, for section 2 and 4, it is quite possible that your neutral axis depth will be in the flange because I'm talking about the section AA, which in my picture are 4 or 5. So if neutral axis at section 4 and 5 will be within the flange, then section 4 and 5 will also be designed as wide rectangular sections, because the T-beam effect will not be coming because section in compression is still rectangular. However, if your neutral axis depth falls within the web, then at section 4 and 5, you need to call the design methodology of T-beam, in which the couple will be made between steel and the flange concrete and steel and the web concrete. While if neutral axis will be in the flange, like picture B on this slide number 5, then the couple will be between the steel and the rectangular concrete which is present in the flange. So interestingly, it is quite possible that even in monolithic construction, although it seems that T-beam sections are present, nowhere you get the T-beam design applied, because over the supports they are already rectangular because flange is in tension. And at interior spans where flange is in compression, neutral axis has traveled within the flange, so the T-shaped compression geometry is not in action as is present in picture D on slide number 5. So it is your chance that how in this example problem different sections are designed, whether all are rectangular or some of the section will be going as T-beam design section. So from this slide onward now, the design steps are started. I want to make one announcement here. The example which I copied from the book by Z.A. Siddiqui, he has proposed a row max for section 0.0075, which actually is mandatory when you want to redistribute the moment. You want to release some moment, then this much strain in the steel is required corresponding to crushing in the concrete. But just to keep the problem simple, and I am not at this moment discussing with you that possibility of redistribution. So I am not following this recommendation. And from this slide onwards, I will be designing it more simple, straightforward. However, later on when you will be taught movement redistribution, movement release, and after releasing the movement at some section, redistributing it at some less stretched sections, then this kind of selection of row max and design will become point of discussion. So what I am going to do is I am starting with the design of this cross section first, which is actually a rectangular beam and highest demand in the continuous beam over the first interior support. Before I start working on the design, there are few important decisions which are made here on this slide, and then onward we will be designing the beam sections, and it's just repetition of what you have studied under the T-beam behavior, under the T-beam design article, that in monolithic construction, when you pour the beam and slab and you are integrating the slabs with the beams in monolithic construction, question will be how much part of the slab will be considered as integral part of the beam. How much the width of the slab, and we use BF as width of the flange. So how much portion of the slab which is cast monolithic with the beam will become integral part of the T-beam. So this BF decision about how much is the width of the flange is very important in order to fix the geometry of the T-beam in monolithic construction. So effective flange width B is selected here because section 4 and 5, where the tension is at the bottom and compression is at the top, we want to know that how much of the flange width will be considered as integral part of the T-beam. So there are 3 recommendations from code, and out of them least minimum will be selected to fix the BF. First is span by 4, span of the beam divided by 4 for interior beams, which comes out to be 1250 as BF. Second is 16 times the slab thickness. It means 8 times the slab thickness on either side, 8 HF, 8 HF. Because it is interior beam, so it has overhangs on both sides. So it comes out to be 16 HF plus BW. So it comes out to be 228 because BW was 228. So 2228 will be the second choice. Third is straightforward, that adjacent panels center to center will become integral part of the beam, which is quite a big dimension, because if we look at the slab system, it means center to center. So it has half of 3.5 on this side, it has half of 3.5 on this side. So you mean that all the slabs center to center will become integral part of this beam which is running over the column. So it is quite unconservative proposal, 3500. So out of them, least, which is conservative, minimum is selected, and then it means we have fixed the flange width of the beams, which will be particularly applicable at sagging regions where flange is in compression. So this BF become important. We need not to neglect the code proposed minimum steel ratio, because if steel selected will be below this, then chances of sudden failure after approaching of modus of rupture when concrete will crack are there. So to avoid sudden failures, code has proposed a minimum reinforcement ratio in the cross section. So while designing them at various sections of continuous beams, we want to keep on comparing the demand with this rho minimum. So when I multiply rho minimum with the web cross-sectional area, considering that I have selected now the D350, so it comes out to be that nowhere I am allowed to go below 266 millimeter square in reinforcement ratio. Uh, let me stop here, or I will have to select discard, so all the text which I have mentioned on the slides will be removed. Discard annotations.